So we're going to introduce this notion of virtual memory, and what I'm going to do is I'm going to rechange what I used to call the CPU address. I'm going to rename that. I'm going to call it the virtual address. So the virtual address is just a fancy name, computer science name, for the address that's generated by your program as it runs on the CPU. The physical address is what the main memory system actually wants coming over those signal wires to the memory chips. And in the middle, we're going to put a memory management unit. And its job is to translate virtual addresses into physical addresses. And the notion is that conceptually, it's a complete mapping. Every virtual address potentially can be mapped into a physical address, but in practice, that mapping is not complete at any given moment. Only some of the legal virtual addresses, okay, you can sort of see, actually have a corresponding physical location. And what we do is the MMU is responsible for mapping some of those. And if I access a region of my virtual address space that does not have a valid mapping to a physical address, I create an exception. I basically say, whoa, it's not in memory. Here's software, you deal with it. The operating system's job is now to figure out, oh, well, you're accessing a page that an address that doesn't exist. Maybe it's on disk. I'll copy it in for you and find a place in physical memory for it. Notice, however, that there's no correspondence between the if I ask for address 0, that doesn't have to line up with physical address 0. And in fact, it could line up with some other region much farther in memory. Everybody sort of happy with that? Now, we could map each byte. We could build something. So we'd have to have a huge, we say, look, you ask for any particular byte, I'll go look up where it really is in physical memory. So that would mean my memory management unit would have to translate any one of 4 billion different addresses into 4 billion physical addresses, or at least tell me that. So it's a big table, or tell me that I don't have such a mapping. So it's a huge table, and that's not going to work very well for us. So the first thing we're going to do is to divide memory up into what we call pages. Not a very complicated word, it's just a collection of contiguous memory addresses. Typically pages on 32-bit machines are on the order of 8K bytes or 16K bytes, something like that. Okay, on 64-bit machines, one of the ways 64-bit machines deal with the very large address space is they use pages that have a couple million bytes on them. And what I mean by dividing up the memory, what we're going to do is to take the address, and some amount of the address, the low order bits of the address, will be the page offset. That'll tell me where in the page I'm trying to get to. And the rest of the address will be the page number. So it'll tell me which page I'm looking for. Right, and where exactly this boundary is one of the architectural parameters of the machine. Okay, so the notion is I'm going to have a map that will tell me, well, I'll get to that. All right, so what's the notion of demand paging? So I'm going to click this up, but then I have an actual demonstration. Wow. I used to love demonstrations. The demonstrations I loved were much more sophisticated than what I'm doing now. So here's all my pages. And initially they're on disk. Now, what a demand paging system does is you say, okay, I'm going to start running my program. PC starts at 0. I need, the information at physical page 0, at virtual page 0. So I'm going to go off and read it off of my disk here, and I'm going to bring it into main memory. And I don't necessarily have to bring it in to physical page 0. I could, I have some other pages, but I find a page, an empty physical page, and I simply say, okay. And then I set up my mapping here so that when you ask for 0, you end up in this physical address. And in fact, that happens for all the 4,000 bytes or whatever it is on this page. Everybody happy with that? Your program runs some more, and pretty soon you do a subroutine call that calls the C library, which is farther up in your address space. Well, I'm going to page that in from disk, and that can show up in physical memory. Notice that the order of pages in the virtual address space don't necessarily correspond to the order of pages in physical address space, right? I mean, they can be higgledy-piggledy. I just have to make sure I remember in my mapping, if you give me a particular you ask for a particular virtual page number, where in physical memory I put that. Everybody sort of happy with that? Okay, so that's what demand paging is. I'm going to bring stuff off of my nicely organized array of pages on disk, okay, organized so I know where to get them, and then I'm going to simply bring them into memory and slowly fill up all my pages, all my physical pages. Yes, sir?
So when start up a computer, it takes so long to start because doing that for a bunch of programs.
Exactly. The first time you type Python, you drum your fingers and say, what the hell is going on? The second time you type Python, it seems instantaneous. The point is that it's already paged in, that's the word they use, paged in all of the interesting pages of the Python interpreter, so they're there in physical memory and ready for you to use. Yes?
So all the previous times we've been talking about addressing with like...
We have always talked about addressing as the address the CPU generates. And today, we've named that the virtual address. Now, you're building a machine which takes the CPU address and wires it directly to main memory. So the Lab 6 beta that you're building does not have an MMU in it. But you'll see that every machine since, somewhere in the mid-70s or even earlier has an MMU for lots of good reasons, which that's what we're exploring today as well. Now, what happens if I need to bring in something and there's no room in physical memory? So here I filled up physical memory. Now I need to bring in this page. Well, we've faced this problem before, right? What do we need to do? We need to throw something out. What should we throw out? Random. Okay, random's a good choice. What's another choice? LRU, and in fact, typically, most of the paging algorithms are LRU. So I take the least recently used page, I guess that was this one, and I put this, do I need to put it back on disk? Under what circumstances do I need to put it back on disk? I mean, there was a copy on disk. If I had done this right, I would have had another stack of these, because I just made a copy of it into main memory. When do I need to actually copy it back onto disk? If it's changed, right? So maybe one thing the MMU should do is not only perform the mapping, but keep track of whenever I do a write to a page, the fact that it's changed, and that's what we call a dirty page that will have to be written back. So you'll see that appear in a little bit.